Bueno, muy buenas tardes para todos. Muchísimas gracias por acompañarnos el día de hoy. Vamos a tener una presentación muy especial. Sin embargo, como de costumbre, tendremos una pequeña introducción sobre Spanish Speaking Acousticians in the Americas Chapter de la Acoustical Society of America. Entonces, después de una corta introducción en español, como les estaba mencionando, tendremos esta presentación que será 100% en inglés, pero tenemos traducción simultánea para aquellas personas que lo puedan llegar a requerir. Por favor, y es importante que utilicemos la sección del Q&A para hacer preguntas a lo largo de la presentación. Se pueden hacer en cualquier momento y se responderán al final de la misma. Y el chat lo podemos utilizar para todo lo relacionado a comentarios que podamos tener a lo largo de la presentación. El día de hoy tenemos una presentación que es la historia de las superficies difusoras de sonido por el doctor Peter D'Antonio. Esta es la junta directiva actual. Evidentemente se pueden acercar a cualquiera de nosotros, lo que puedan llegar a requerir para que nos acompañen en este capítulo, que una de las ventajas que tenemos es no necesariamente hay que estar como miembro de la ASA. Pueden pertenecer igual al capítulo a nosotros de Spanish Speaking Acoustician, que es una comunidad de habla hispana completamente gratuita, en la cual nos pueden acompañar para compartir diferentes contenidos. Y adicionalmente, todo lo relacionado a nuestras redes sociales, tanto lo que es la página web, Facebook, LinkedIn, YouTube, nuestro correo electrónico y una conversación muy interesante que nos pueden acompañar en la plataforma de Discord. Spanish Speaking Acousticians es una comunidad que fundamos colectivamente para poder conectar varias personas a lo largo del territorio latinoamericano e incluso iberoamericano, ¿no? Todo lo que somos hispanohablantes de todos los temas relacionados a la acústica y afines. Y quiero darles un pequeño recordatorio. Tenemos la competencia Royster, que está por cerrar el próximo 27 de junio. Aquí pueden ver algunas de las políticas, los premios y demás características de esta competencia. Estamos empujando bastante para nuestro territorio, pero podrán encontrar más detalles directamente en nuestra página web para aquellos que estén interesados, luego que la fecha límite ya es para el 27 de junio. Y los próximos eventos que tenemos para el 7 de julio, 5 de la tarde de Bogotá, Lima, Quito y 6 p.m. Eastern Time, tenemos cavitación ultrasónica para el café por Francisco Trujillo. Estén lógicamente pendientes a nuestras redes sociales para que tengan conocimiento de todas las actividades que desarrollamos con nuestro capítulo. Ahora bien, con relación a esta actividad en particular, tenemos interpretación simultánea. Significa que a pesar de que la presentación es en inglés, van a poder tener una traducción simultánea en el canal de la parte inferior. En todas las sesiones de Zoom van a poder encontrar en la parte inferior, al lado del Q&A, un globo como el mundo, donde dice interpretación. Ahí van a poder seleccionar el idioma de preferencia que puedan ustedes tener. Finalmente, les quiero recordar utilizar la sección de Q&A para hacer las preguntas y el chat para todo lo relacionado a los comentarios. Ahora bien, esta presentación que nos ofrecerá el doctor Peter D'Antonio será la historia de las superficies difusoras del sonido. Básicamente nos describirá la evolución de la técnica de medición que llevó básicamente a lo que es la norma ISO 17497-2, luego que son mediciones laboriosas, tediosas como tal, pero que se demostró a través de la respuesta polar y el coeficiente de difusión se pueden simular la precisión a través del método de elementos de contorno. Entonces el doctor Peter D'Antonio también nos demostrará un poco sobre el nuevo programa de ondas llamado Virgo, que puede simular el rendimiento de cualquier superficie reflectante o híbrida a partir de un modelo CAD en 3 dimensiones. Durante la presentación, lo interesante es que también se demostrarán varias aplicaciones de este proceso. Y finalmente, tenemos 2 novedades muy interesantes. Lógicamente, una breve introducción que haré del Peter D'Antonio, que evidentemente yo sé que muchos de ustedes ya lo conocen muy bien. Pero saben ustedes que el doctor Peter D'Antonio, además de haber sido una de las personas que más aportes tal vez ha desarrollado en relación a todos los estándares en función de mediciones de los estándares para ISO y demás estándares para mediciones de materiales acústicos, todos evidentemente conocemos el libro de Acoustic Absorbers and Diffusers, Theory, Design and Applications, que trabajó conjuntamente con Trevor Cox. Adicionalmente, pues ha participado en varias publicaciones, entre ellas se destaca el Master Handbook of Acoustics, además de que, como ustedes bien saben, fue chairman también del subcomité de AES para acústica y ha trabajado también en los estándares del AES 4I de 2001 para estandarización de coeficientes de difusión, también miembro para todo lo relacionado entre los grupos de trabajo de la ISO, entre los estándares de ISO en relación a los coeficientes de dispersión y adicionalmente a la estandarización de coeficientes de difusión. Profesor adjunto adicionalmente eso al Cleveland Institute of Music. Además de eso, es un fellow member de la Acoustical Society of America y la Audio Engineering Society. Y desde el 2012 ha sido un inductee dentro de lo que es el Salón de la Fama de Tech. Y además de eso, es presidente y fundador de Chesapeake Acoustic Research Institute y adicionalmente a eso, fundador, como ustedes bien saben, de RPG, su compañía que vendió desde el año 2017, pero que generó demasiados aportes y sigue trabajando también todo lo relacionado a investigación y desarrollo, y director de investigación para Ready Acoustics, que también trabaja todo lo relacionado a la itinerancia de software, servicios de software basados en comportamientos de ondas. Entonces, es breve y me quedo corto con todo lo que podríamos hablar del doctor Peter D'Antonio, pero nos sentimos honrados de tenerlo. Y como un valor agregado, tenemos justamente a John Storyk, fundador y socio de Walter Storyk Design Group, que nos hará una introducción a la presentación del doctor Peter D'Antonio. Entonces, muchísimas gracias y pasaré al canal de inglés y darle la bienvenida a nuestros participantes. Well, so thank you, Peter. Thank you, John, for joining us. And we are more than pleased to having you here. People don't want to hear me, they want to hear you. So I give you the word so that you can guys start with this wonderful presentation.
All right, thank you. Thank you, Andrés. Bienvenidos todos. Es un honor estar aquí, básicamente, para presentar un querido amigo y compañero de toda la vida. And 1 second, I gotta turn off. Now I'm hearing myself in English. Practicando mi español contigo. Y Peter es nuestra búsqueda mutua de la arquitectura del gran sonido y específicamente para mí en los estudios de grabación. Es un amigo de 40 años. Me gustaría poder hablar contigo en español, pero como puedes ver, es un poquito limitado mi español. Básicamente, mi español es bastante bien para comer. Vivo en México 3 meses cada año y necesito mucho más practicar. Entonces, otra vez, gracias para estar aquí y voy a continuar en inglés. So, excuse my Spanish. I need more practice, but in future days, I hope to be able to do an entire talk in Spanish. Peter and I have known each other for what seems like an eternity. It's an honor to simply introduce him and maybe get the talk started. Let me share my screen really quick, if you will. I got the easy job. So this is the title of what we're going to be discussing, but oh, what a surprise. We're going to try to discuss a few more things as well. Peter's work in diffusion is well known, and you'll hear all about it in summary, or as best that he can do in the limited time. over the 30 or 40 years we've known each other. My efforts have simply been to use the toys and the tools that Peter and others have provided with us to design recording studios. That's the subject of another talk. My start is there. That just means I'm old. Many of you know about that. These are the kinds of rooms that I've been able to design with my team over the years, using the toys and the tools that people like Peter, and Peter specifically, have given us. I've chosen some slides that basically have a lot of diffusion, and most of these have RPG products in them. This is my way of thanking Peter and my way of reminding all of us that we should all thank Peter. I'm not really going to talk about these pictures, but they're here to just set the stage to remind us that at the end of the day, all this theoretical work that Peter and others like Trevor Cox have done need to be implemented in real rooms, and they can be fantastic, they can be amazing, and the goals are all the same. The goals are, we all have the same goals, which is to get our rooms to sound accurate and as perfect as possible, to allow mixers, producers, artists to make music. That's the goal. There is no other goal. At the same time, we're allowed to have some architectural fun. We've made diffusers in almost every material, clear plastic diffusers. Here's an instance where we needed to see through them. Diffusers have led to flat diffusing surfaces. Peter will talk a little bit about that. They have found their way into larger installations, okay, such as these very large rear walls and control rooms. And of course, they've found their way in very strange forms and strange shapes, concert halls. I'm sure Peter will talk a little bit about that, okay. And most recently, and this is the sort of added, a little bit of an added bonus that I hope Peter will talk about. It's been an honor to have Peter be the director of research of our company, and now our separate companies, research into wave-based analysis, which has resulted in Nairo software. This is our team right here. You can see Peter is the director of research. A very good friend of mine, PK Pandy, who founded GC Pro, and myself are the directing partners. And then we have a team of researchers and developers. This is the subject. Peter will touch on it ever so gently, I hope. And it's very exciting. I think it's the future. And we're going to, in addition to diffusion discussions, I'm hoping that Peter will give us a little bit of a glimpse into where we're going with this company. So again, thank you for allowing me to introduce Peter. Peter, I'm officially thanking you for 40 years. I don't know if we're going to get 40 more, but we'll go 1 year at a time. And with that, I will stop sharing my screen, and then I will hand I suspect, directly over to Peter, who will continue in English.
If I can figure it out.
Everybody, I promise to be better in Spanish. We see the screen. There you go. Great. Thanks, Peter.
Thank you very much, John. The pleasure has been mine. So what you're seeing here is one of the most recent developments. You're seeing the actual three-dimensional scattering at different frequencies from the surface of this skyline here. And I'll talk more about that, but I'd like to begin with just a short story. John and I do go way back, and we have different beginnings. Talk a little story about what led to this presentation, an event that happened 40 years ago. In 1980, I planned to build a professional recording studio to record my original musical compositions. And so at the time, however, I was a physicist examining the three-dimensional structure of matter in various phases using electron and X-ray diffraction techniques. Since my formal education was not in acoustics, actually, it was in chemistry and physics, I consulted the scientific literature the way we would normally do. And I was surprised that I didn't find any publications on recording studio design. But I did find an article in an audio magazine about a live end dead end approach by Don and Carolyn Davis that you see there. And very coincidentally, at lunch, I came across another article by a very famous person called Manfred Schroeder on these new surfaces called reflection phase gratings that he suggested to improve the acoustics of concert halls. Now, while my interest in concert halls wasn't very high at the time, this article really piqued my interest because he was describing essentially two-dimensional periodic lattices, which scatter sound in the same way that the three-dimensional periodic lattices that I've been studying scatter electromagnetic radiation. This was the resulting studio that I built in 1983. And so with this information, I set out to design a new concept for recording control rooms using a mathematical approach, which we usually do in looking at the boundary conditions, they being an anechoic chamber and a reverberation chamber. And in a large room, generally you see an initial time delay that Baranek was mentioning. And so I wanted to create that initial time delay in a small room, which I did using, by controlling these early reflections. And I created the diffuse end or the live end using reflection phase grating diffusers. And so you see that the goal was to simply remove these early reflections and convert this very irregular temporal response to a very dense and linear decaying in dB diffuse response. And never expecting that this would lead to formation of another company called RPG Diffusor Systems in 1983. So if we fast forward to 2017, a slide that John had shown you, John P.K. Pandy and I established a new company called Ready Acoustics to develop software to iteratively optimize this design in critical listening rooms. And so this presentation begins with a brief description of this first optimization tool called Nero, developed with this incredibly talented team that you see here. And then I'll go on to describe the theory, design, and evolution of the current state of the art of sound diffusing surfaces and show some applications in a wide range of environments. So to address the entire frequency response, we began by addressing ways to optimize the low frequency response below a frequency called the Schroeder frequency, which is related to the square root of the reverberation time over the volume. And using a finite element method, now we originally used the boundary element method. FEM gives us a little more capability and runs a bit faster to optimize the frequency response and simultaneously the speaker boundary interference response. To address the frequencies above the Schroeder frequency, we have developed a geometric model so that we could control the reflections and also predict the reverberation time in the room. And so what the goal really of this is what you're looking at is the pressure distribution in the room, both on the boundary and within the volume of the room. You see the two loudspeakers here. And the goal is to really find a sweet spot for the listener and for the loudspeakers, where the pressure is basically at a minimum or at a median pressure, I should say. So the way we accomplish that in very few words is we minimize 3 fitness metrics. What we are doing is that we simultaneously optimize all of these metrics using a multi-objective genetic algorithm to obtain the optimal geometry and the locations of all of the speakers and the listeners over a listening grid volume that you see here in this color to account for the movement of the mixing engineer. And so we minimize the standard deviation of the frequency response function and the speaker boundary interference. We minimize the spatial standard deviation over the various positions that a mixer might move to. And lastly, we minimize reflections in the reflection-free zone. In other words, we want to minimize all of these first and second order reflections to create an optimal frequency response. Once we do that, we can then compare the untreated room, which you see here, and the light blue is basically showing you the deviation within this spatial volume that the mixer might move within. And it's essentially an extruded rectangle. It's about 1 meter wide, and a given height and depth, it's variable. And so you can see in the untreated room, the temporal decay is really long. The reverberation time is high. And once we treat the room, we then further minimize the peaks in the frequency response, and we control the temporal decay, and we basically create a very uniform reverberation time over the entire band, frequency band. And so what we have recently worked on is we combine the wave acoustics model with the geometric acoustics model so that we can create a full bandwidth impulse response with which we can oralize the process as we optimize the environment. We can compare the process before treatment, after treatment, and get some idea of the importance of each of the steps. So we've compared this in a room at WSDG, and you can see the agreement is really quite good. And of course, we've worked on maybe 50 or so rooms at this point. This is one of the more recent ones for which we actually have in situ measurements. And you can see that the measurement and the prediction of the left subwoofer is really quite good. And this is a very, very complicated geometry. So now we can move on to the diffusion theory. And it all began with what is called a reflection phase grating, which is where I got the acronym RPG, in case it wasn't apparent. And what you're seeing here is 2 periods of a reflection phase grating with a series of wells of different depth separated by dividers. And the phase, these different well depths create a phase change. And when all of these, waves combine and interact with the incident sound, you get uniform scattering. And so thank you, Andres, for mentioning the book. But if you have any other questions, you can find them in the 3rd edition of my book with Professor Trevor Cox. So let me just give you a very quick description of how you generate a number theory sequence. In this case, it's a quadratic residue sequence, which was one of the most utilized in the beginning. Of course, you have primitive root sequences, you have any number of number theory sequences, but it's required that they have a flat power spectrum. And so for a prime number of 7, say, what you do is you construct a chart here where you have n, which is an integer. Then you square that integer, and then you take the modulus of that squared integer with the prime number. And all that means is you can go through here, 2 squared, 3 squared is 9, 4 squared is 16. And what you find out is that if you divide, what is a modulus? So what a modulus is that it's the remainder after you divide the prime number, after you divide n squared by the prime number. So for example, in the case of 9, 7 goes into 9 once with a remainder of 2. So we're really interested in the remainders because the remainders are more important because they relate to a shift, a phase in the frequency, more so than if you just have an integral number of periods. You don't get constructive interference in that case. And so the other thing you find out here is that this sequence is periodic. You notice that when we get to 7 squared is 49 divided by 7, goes 7 times, but there's no remainder. And that's the beauty of these sequences, is that they are periodic sequences. And it turns out, as you study this, while this is the raison d'etre of why these diffusers work, periodicity is also a problem.
On it.
Also a problem, which my watch just said something to me. And if you want to
Working on that.
if you want to determine the well depth, if you want to determine
Something went wrong. Please try again.
if you want to determine the well depth, you basically simply take the sequence number multiplied by the wavelength of the lowest frequency divided by 2 times the prime number. So then the question becomes, once we develop these surfaces, the question became, well, how do we measure them? And what you're seeing here now is an FDTD finite difference illustration of how these various delayed waves combine at the face to create uniform scattering. And so this is the evolution of what I call the goniometer. Goniometer is just a device to accurately measure the angular pressure or the angular scattering, which I used in my X-ray diffraction career. So between 1983 and 93, I used one microphone that I moved in 5-degree increments around an arc and one preamp in a TEF analyzer. This was in a large sports venue. Once we got asked to leave there, we moved to my son's high school gymnasium. And after we kept getting evicted, I thought perhaps I should create a scale model goniometer. And this was the first 1 to 10 scale model goniometer on a tabletop at RPG. We then evolved into having 32 microphones, still with 32 microphones, but still using one preamp. And then finally, we moved over to using a workstation, a digital audio workstation called Reaper, in which we simultaneously measured all of the scattered sound, because now we have 32 microphones and 32 preamps. And so this is the latest version of the goniometer at RPG. And so what you get is you get these 32 direct sounds, then you get scattering from the sample of interest, and then you get the room interference, because I didn't have an anechoic chamber, so I just built this into my office using a ground plane, using microphones mounted right on the ground plane to remove the ground plane. And so it's called pressure zone microphones. And so what you have to do then is you have to extract this scattered sound. Hopefully you can see my mouse. We have to extract this scattered sound from the direct sound and the room interference. And so we do that by measuring the scattering. Then we take the sample away and we measure the background, and then we deconvolve that with the speaker microphone transfer function, so that we remove any irregularities of the speaker and microphone and isolate the scattered sound. And once you go through that process of isolating the scattered sound, and then we just concatenated the scattered sound at different angles, transform those into the frequency domain, and then take a third octave polar response, and then calculate the diffusion coefficient. What the diffusion coefficient is the autocorrelation of these polar responses, expressed mathematically here. And so you can see for a flat panel, if the sound is incident at 60 degrees, it will scatter. at 60 degrees on the other side of the normal. Whereas for a diffuser, you have uniform scattering. The objective is to get uniform scattering at all angles of incidence. And then we have to normalize that data because at low frequency, the sample becomes a point source. And so we normalize it. We normalize it by the scattering from the flat panel. Now, what I'm showing you here is the new Acoustical Research Center at RPG. We have an experimental measurement laboratory, which is a 285 cubic meter reverberation chamber, a 7-ton impedance tube that has a square section of 60 centimeters, which measures from 20 hertz to 200 hertz. And we also have the goniometer. We recently have created a virtual simulation lab that I'll talk about in a little bit. And we also have a virtual education lab, which we run posts on LinkedIn, which I'll talk more about later. So in addition to the experimental goniometer, we now have a virtual goniometer, which we call Virgo. And we can now simulate the scattering from any surface simply from a 3D CAD file. And we can do that in 2 dimensions to simulate the 2D ground plane goniometer, which we use 5 speakers and 180 microphones with a 1 degree increment. And now, for the first time, we can actually measure the 3D polar response using this virtual goniometer, Virgo, where we have 13 sources, which are specified in the ISO 17497-2 standard. We have 4,295 microphones on this grid that you see here. And then the sample goes in the middle. And we have microphones at 1.6 degrees in both azimuth and in elevation. And this was a 3-dimensional goniometer that one of my students actually built in 1998 at Salford University. So we now have a virtual goniometer. And so as a proof of performance, we just compared the diffusion coefficient and the polar responses from a single hemicylinder. And you can see that Virgo predicts a very close agreement with the experimental diffusion coefficient. And you can see that the polar responses at these 3 frequencies are very, very similar. There's a little more resolution in the Virgo prediction because we have so many more microphones. That's also true for different angles of incidence, for the 5 angles of incidence. And so you saw the prediction, the polar scattering from the surface of, this is a product called a bicubic. It's a 1.2 by 1.2 meter glass reinforced gypsum surface. And this surface contains 76,000 elements. And the only way that we can do this is by doing it in the cloud using a distributed cloud cluster, which I won't go into details at the moment because we have a lot to talk about. So as I mentioned earlier, you can't just simply take a diffuser and periodically array it on a wall because it generates grating lobes, which degrade the performance. But the first task that we addressed with respect to a reflection phase grating diffuser is to increase its bandwidth. So just like a loudspeaker, one loudspeaker has a certain range of frequencies. You add a tweeter, you add a woofer. And so we did the same thing with a diffuser, and we created what is called a diffusing fractal, or we called it a diffractal. And I'll explain more about that as we go. The second problem that we had to deal with was that whenever you have a number theory sequence, all of the well depths are predictable from any one depth that you know. And at integral multiples of the frequency, all of those well depths are in phase. And so you get a specular reflection. And so we had to modulate that surface. And I'll describe all this in details. And the way we modulated it was by taking an asymmetric shape, in other words, a shape that you could flip, and using a prescription based upon an optimal binary code, a Barker sequence, we can convert a periodic sequence which has problems to an aperiodic sequence which is missing those problems. So the first thing we did was to create a fractal. And there's many ways you can create a fractal from the Koch fractal that you may be familiar with. You simply keep reducing the scale. This became a little too hard to make. So this is the way we created the fractal. I'm showing you a picture here of Manfred Schroeder at an AES convention where we first showed the diffractal. He was very proud of it. And actually I met him on a plane going to Penn State at a conference. And he called his publisher and halted publication of his new book and very graciously included our work on the diffractal. Now, as I mentioned, when you have a periodic array based on a number theory sequence at integral multiples of the design frequency, you get a specular reflection. Then you get a good diffuser, then you get a specular reflection. So we had to develop a modulated surface that does not have quantized well depths. Okay, and those are called Modffusers and Modffractals. I'll talk about that in a minute. So these are the grating lobes that I'm talking about. Whenever you have a periodic array, there's a formula where m is an integer. This is a wavelength. This is the width of the period of the surface. And theta is the scattering angle. And so it's a Virgo predicts very, very accurately these grating lobes, as you can see here. This is an array of 4 hemicylinders. So the way this happened was we created this Modfuser having non-quantized well depths. And the way you get rid of the grating lobes is to flip it because now we need a 0 and a 1. And so this is a 0 and this is the 1. And so based on this prescription, which is a Barker code for 5 units, we mount, it's basically a mounting instruction. You mount the first sequence, you flip it, then you have 3 sequences that are the unflipped version. And when you do that, you dramatically increase the diffusion coefficient, this blue line from the red line. And so what has happened over the years is we started out with a QRD that has a very limited bandwidth. And if you have a periodic array, you get grating lobes. And then we created the diffractal. And so we extended the frequency response. And then we created a Modfuser where the well depths, you see these well depths are no longer quantized. It's no longer a 0, 1, 4, 0, 1, 4, 2, 2, 4, 1, 0. They're all very different. And then we converted that Modfuser into a Modffractal, which is the current state of the art. So in 1984 was the first time that I was introduced to what was called a TEF machine. And we measured the actual time response from a QRD and a PRD, and you can see them here. So I was pretty amazed. You can see that. And a good diffuser, basically, just so I can mention this, it has both a time distribution, a time diffusion, but also a spatial diffusion. There are many ways you can get a spatial diffusion, like with a hemicylinder, but it has a horrible time distribution. So those two are very important. And then we got lucky in 1984 with Bob Todrak, who was designing a new studio for the Oak Ridge Boys. And so we got to put in a mirrored diffuser. And then, as John showed, there's been a multitude of of diffusing surfaces, and you can go to the WSDG website and look at your heart's content. But we also got lucky in 1989, just a few years after we started the company. We were asked to improve a problem at the famous Carnegie Hall, and they had a very strong slap echo off the back wall. And so we created a custom diffuser and eliminated that problem. And I just noticed on a TV show called Sunday Morning that in 2014, at the 125th anniversary, the surfaces were still on the wall. So I guess they're still working. And then, as time progressed, people got tired of looking at RPG diffusers, and architects wanted a flat surface. So we created what is called a binary amplitude diffuser. And you have areas that are reflective and areas that are absorptive. And you can see, based on the Huygens waves, that you eventually can change the direction of the waves when you get that interference. And then we either covered it or we didn't cover it. But just a very quick discussion about how you can do this. Whenever you have a one-dimensional sequence, whether it's a maximum length sequence or a quadratic sequence or a primitive root sequence, you can fold that into a two-dimensional sequence if, and you can't do it with a QRD because the number has to have two coprimes. So in the case of 15, the two coprimes are 3 and 5. 3 times 5 is 15. And so you create this matrix, this 3 by 5 matrix, and you begin filling the holes. So you take this one and you put it here, then another one, and now this 0, where is the 0 going to go? Well, the 0 is going to go down here, but because this is a periodic array, the 0 in this unit cell is the same as this one up here. So the 0 goes here. And then the next one goes here, and the next one would go here into this other unit cell, but it's the same as the one over here. So that's the way you convert a one-dimensional sequence into a two-dimensional sequence. And we can do this for a primitive root diffuser because this number is 1023, which is a 31 by 35 31 by 33 sequence. And as John showed, we've had all kinds of installations of both the covered and the uncovered binary amplitude diffuser. So moving forward again, people get tired of the same visual look, and working with creative people like John and other architects, we needed to create a surface that did not look like a reflection phase grating. And so what we did was to create a shape optimizer program. It's a boundary element program in which we start with a shape that the architect would have in mind. We parameterize that shape, okay? And then we look at this, we calculate the scattering from that shape, and we iterate until we get a uniform scattered response over a hemisphere in the far field. So the X's are the sources and the squares are the observers. And you're looking at literally the program in action, changing those shapes, evaluating the diffusion coefficient, and continuing until we get a satisfactory answer. So in order to do this, we optimize these shapes, both step shapes, like the skyline, or an opti-step. And we then created scale models. We had a very early version of a 3D printer at RPG. And so we created a 5th scale sample of these various surfaces, measured them on the goniometer, and then manufactured them. And all these shapes are available in glass reinforced gypsum and in curvilinear wood. And so we started working we began in recording studios, and then we started working in performance spaces. And so this is an overhead canopy at Massachusetts Institute of Technology Kresge Auditorium, in which the pressure on the stage moving from rear to front was very uneven. And so what the shape optimizer did was to shape this overhead canopy until the pressure moving back to front stage was uniform. We then moved to optimizing audience canopies. So this is the shape optimizer for an audience canopy. And so what you see is, here's the sources on stage, and here are the listeners in the auditorium. And so the architect or acoustician would create a number of canopies, both on the stage and the four-stage canopy, which is here, which handles the first area of the auditorium. And then what the program does is it proceeds to optimize these shapes, these curvilinear shapes, until the pressure across all of the audience seats is as uniform as possible within the architectural constraints. We then had another type of a problem in which the sources and the receivers are both on stage, and the receivers are in the audience with a very sparse overhead canopy. And so the diamonds are the musicians' instruments, the squares are the musicians' ears, and these squares are the audience's ears. And so the program basically optimized the shape and the tilt of the canopy elements for a uniform sound pressure level at all optimization points. And here you see the River Center for the Performing Arts, which is the project that was. And here you see a whole collage of shape optimized wooden surfaces and shape optimized glass reinforced gypsum surfaces, both as clouds, mostly as clouds here, as rear walls. Another problem cropped up in which a project had a concave surface in a performance hall at the Edwina Palmer Hall in England. And so all of the energy was focused at one point, the focal point of the concave surface. And so we created another program called an amplitude modulator, in which we basically wiggled that concave surface and then created a glass reinforced gypsum version of, this is the output of the optimizer, to essentially remove this focal point so that the energy was uniformly scattered to all of the listeners. The last thing we worked on were acoustical stage shells. And I taught at the Cleveland Institute of Music, and we had this program there, a pretty long program in which we did in-the-ear recordings of the musicians, and we had several different ensembles. And we also used a binaural head. This is Wade Bray at Head Acoustics. And so we measured the performance on stage with different orientations of the shell. And then Jack Renner, who's the founder of Telok Records, also measured the sound in the audience. And we eventually came up with a configuration of this shell, which had optimal performance both on stage and in the audience. And this was the first version of what we call the Variable Acoustics Modular Performance Shell, or VAMPS, as I named it. And it provided very uniform scattering. This is a lot of good temporal diffusion here. This is the Cavani String Quartet at the Cleveland Institute of Music. This shell evolved very dramatically into what you see in these various performance spaces. This is a atmospheric theater. This is Corning Glass in New York. This is actually a project we did with John at the Murray Art Center. This is Sacramento Philharmonic Hall, and this is First Baptist Church. So, as I like to say, this is just the beginning, and I invite you to visit my LinkedIn page, in which we have weekly posts, educational posts. And we recently posted a Ready Acoustics page on LinkedIn. Rinaldi Petroli just put this up. And I also invite you to listen to my music. I have another life as a musician. And with that, I want to thank you for listening. And that concludes my presentation.
Peter, thank you very much for your presentation. We can now move forward into the questions from the audience. So if anyone has any questions, they can move into the Q&A section, and not exactly into the chat, but into the Q&A.
Sure.
We have one actually.
Okay.
So
I guess
for the moment, people is being shy, but I know there's a lot of people that have some questions. So Orlando asked if, will you share links to the information that was presented? So we are gonna have this uploaded to YouTube, but Peter also mentioned different places where they're sharing a lot of information, but maybe if you could share with people where they could find more information regarding your presentation.
Well, this presentation was created specifically for this talk. So the best option is to look at the recording that you created. Does that answer the question?
Yeah, a little bit. I'm sure they could find more information regarding diffusion and what.
Oh, okay. So you can, okay, I see. So you can obviously go to the RPG Acoustical Systems webpage, and you can visit my LinkedIn page, where so far I've described the experimental lab, and I've described the virtual goniometer. And in a week or two, I will begin an acoustics curriculum on many of the topics that I've covered here. So that might be an easier way for people to learn about it, because it'll be a very, be presented in very understandable chunks. And of course, there is my book, but I know it's not in Spanish, so I apologize. And if anybody has a question, they can always simply email me. I have many PowerPoint presentations that I can share with people that have an interest in it.
We have two more questions. So Jamie Angus, sorry. Does the use of curvilinear diffusers reduce the time spread compared to the Schroeder style gratings?
No, they're both, the goal in all of the optimizations, the goal is to simultaneously optimize the temporal scattering and also the spatial scattering. And you can tell that from the diffusion coefficient. So the answer is no. Both are useful. The only difference is really architectural. So most of the curvilinear surfaces have been used in performance spaces. where you're a sufficient distance away from the surface. And most of the reflection phase gratings have been used in recording spaces. However, I have showed some, like in Carnegie Hall, and I didn't show you the Fritz Philipp Music Center in Eindhoven, Maryland uses reflection phase gratings. So they're both useful. It just depends on the architectural motif.
Andres and Peter, I have to go. Everybody, thank you. I have to teach at Berkeley, and I hope to see everybody soon.
All right,
Peter,
John.
thanks.
Thank
Peter,
you. Thanks
I'll talk to you tomorrow, as I do every day.
Yeah, thanks for your support over the years.
Yeah.
Thank you, John, for joining us.
Andres, otra vez, amigo. Okay, claro que sí.
For sure, John. Have a great one. Bye-bye. Adios. We have a question from our former chair from the Spanish-speaking acousticians, Fernando del Solar. How far away should you be from diffuser to perceive the diffuse field correctly?
Right. That's a very good question. And there's actually a hierarchy. So let me just run through that. So in terms of proximity to the wall, in terms of closeness to the wall, you start with an absorber. You can obviously be reasonably close to an absorber. And then you would move to a binary amplitude diffuser. From there, you would then, and as I mentioned, these surfaces, you're moving, kind of a foot or two away, farther away from the wall. And then you would go to, say, a QRD and into a Modfuser and then a Modffractal. So typically for a Modffractal, you'd want to be about 10 feet away. Now, what I forgot to mention is that you can be closer to a two-dimensional diffuser, like an omnifuser or a skyline, because the scattering from a two-dimensional diffuser occurs over a hemisphere. So the energy in any one particular direction is reduced significantly. So again, with the analogy, it would be a binary amplitude diffuser, a two-dimensional diffuser, and then a Modfuser or a Modffractal. But when you're in a small space like a recording studio, it's very difficult to get farther than 10 feet away. So we try to, when we're doing the Nero optimization, if we're getting too close to the back wall, we would then prefer a two-dimensional diffuser. Whereas in a normal situation where you have 10 or 12 feet, a Modffractal would be good to use. And I know a lot of people use flutter-free, but I would recommend not using flutter-free because the bandwidth is very, very limited. It's okay in certain applications, but try to move to one of the surfaces that has a much broader bandwidth. So if I've answered that question, let me know.
Yes, perfect.
Okay.
We have a question from Ricardo Patraquim, and he wants to know your opinion on the use of machine learning in optimizing diffusers.
Yeah. I wish I knew more about it. But the Virgo, the virtual simulation, the virtual goniometer is sort of one step in that direction, where we're basically predicting the performance. And then, of course, we would have to put that into an optimization loop, which I have done in many of the optimizers that I've mentioned to you. And while I confess that I don't have much of a background in machine learning, I think it would probably be the next step.
We have a question from Cuauhtemoc Mendez. Has there been any success using other fractal shapes? What about 3D shapes like the Menger sponge? Thanks a lot, Professor.
Yeah, we looked at a lot of fractal shapes. And I'm just trying to think back to the evolution. We found that not all fractal, let me say this. If you do it properly and you can get enough generations of the fractal, then it's good, because the fractal, basically the intention of the fractal is to improve the bandwidth. So for example, you may have seen in some of the Nero reports where we go one step further than the Modffractal. So let me just try to very slowly describe that. So we went from the Modfusor, we went from the QRD, which is kind of like a mid-range loudspeaker, okay? And then we went to the Modffractal, which is like adding a tweeter and forming a two-way speaker. And then we went to a translated Modffractal, where we take the Modffractal and we translate it in using the depths of the QRD to get the woofer. So a fractal on its own is very useful, but it depends on what bandwidth you want to obtain. I was interested in Penrose tiles as an aperiodic array, which could work, something I'd like to get back to at some point. But yeah, the whole purpose of a fractal is to create this, these generations where you take a shape, you scale that whole shape to one feature of the generator, and you get another shape, and then you scale that entire shape to one feature of the second generation. And so now you've got 3 generations, each creating, each covering a different bandwidth. So whatever shape you want to use to try to do that, I think it would be useful.
Rafael Pereira asks, what audio signals are used nowadays for measuring and why?
I use an MLS sequence, a weighted MLS sequence. You can use a logarithmic sinusoidal suite. I find that the MLS sequence works reasonably well. And it works well with respect to noise, getting around noise that might occur. In the reverberation chamber, I have to use an MLS sequence. I have to use an MLS sequence because we measure 3 speakers simultaneously. In other words, to adhere to the ISO 354 standard, you have to have at least 3 speakers and 6 microphones. In other words, you have to have 18 impulse responses that you measure in the room. So rather than turning one speaker on and measuring 6 impulses, and then turning the next speaker on and measuring 6, and the next one 6, we simultaneously excite the room with the 3 loudspeakers at one time. You can't do that with a swept sine wave. If you're doing it one at a time, then a weighted swept sine wave or logarithmic sine wave are perfectly useful. I hope that answers the question.
We have an anonymous attendee that says, what's the definition of flutter-free diffuser? So maybe if you can talk a little bit about the flutter-free diffuser.
Oh, flutter-free diffuser is just simply a 5-inch wide QRD diffuser. It's just a narrow diffuser that was intended to control high frequency flutter echo. And it's just simply a 014222410 QRD sequence in in 5 inches, if I could convert. It's like 128 millimeters wide. And it is what we place in the wells of a QRD to create the diffractal. Okay, so the QRD wells are 128 millimeters wide. And so instead of having a flat board on the back of the well, forming the well rather, we put a piece of the flutter-free in there. And so then we have generated like a 2nd generation diffuser. We have a woofer and a tweeter. And the reason I say to be careful about using flutter-free is because when you have a periodic array of flutter-free, you are degrading your frequency response because of the grating lobes. So it's a pretty surface, and I know people like it. We created a better version of flutter-free called flutter-free T, flutter-free_T, which if you go to the RPG website, you'll see that it has a much better bandwidth. And it's also asymmetric. Okay, this is a very important point. Flutter-free T is asymmetric. In other words, you can flip it, just the way I showed you how you can flip the Modfuser. So if you take flutter-free T, you can basically flip that panel around, even if you don't do it according to a prescribed optimal binary code. Even if you randomly flip the plank 180 degrees, you will be generating an aperiodic sequence. And so you won't be degrading your diffusion coefficient. So it's really an important thing to know about diffusers. That's a good question. Thank you.
Renzo Pangarelli, he's asking if has ever been used variable diffusion systems.
The answer is no. I had a student who created a variable diffuser. In other words, the wells were optimized. The well depths were optimized. And so depending upon what frequency bandwidth you wanted to optimize, the well depths could be automatically converted to the proper depth. But I never really saw a use for that, so we never really commercialized that. But it was a pretty device. you could watch the wells dancing front and back.
Jamie is having another question, and he's asking if isn't a curvilinear shape almost like an infinite fractal?
That's a good question. Is a curvilinear shape like an infinite fractal? I don't think of it that way. I'm trying to understand what the reason for the question was. Because a fractal is composed of, scaled versions of the original base shape. And so a curvilinear shape is an optimized shape. It's one shape. The original description of a fractal by Mandelbrot was the coastline of England. So let's say you're up at 30,000 feet, however many meters that is, and you see the coast of England. As you come down to half the height, you still see a scaled version of the coast of England. As you come down lower, you still see a lower scale version of the coast of England. Now, the reason I mentioned that is because I'm thinking of a diffractal. I'm thinking of a curvilinear surface. As I look at a curvilinear surface from a certain distance away, and I approach that surface, it still looks like the same surface. I don't know if that is a good explanation or a good answer to the question.
No, it makes sense. It totally makes sense what you were saying. And Jamie once again has a question that he says that I think you could possibly use spherical harmonics to reduce the number of measurement positions on a memispherical goniometer measurement.
Yes, I think you can. People use spherical harmonics in virtual simulations, obviously, and in sound systems, and I've never worked with that, but I think it might be an interesting thing to research. And if I could just say this, I mean, if anybody has an idea of an interesting research project, I'm very happy to mentor, master students or PhD students. So, if you have a research project and you want to pursue that as a graduate student, or even as an undergraduate, I'm happy to collaborate with it, because I learn a lot from that experience. And so.
And we have one last question from Ricardo Patraquim. The waveform diffusers don't suffer problems with the lobes when using several elements?
Yeah, okay, so the waveform diffusers are asymmetric. Okay, so when you're using a waveform diffuser, you should flip the surface to form an aperiodic array. And then I showed you a picture of the bicubic. Okay, the bicubic is a 1.2 by 1.2 meter square surface that has sort of like a contour plot.
Mm-hmm.
And what we did for that is we optimized the interior surface, but we morphed that such that the four perimeter areas have the same shape. So what I'm trying to say is that you can take that bicubic and rotate it 90, 180, 270, however many times you want to flip it, it will still look continuous at the intersection, because the perimeter of the bicubic is the same on all four sides.
Mm.
It's only that when you come toward the interior that the surface is aperiodic, is asymmetric rather. So there's a difference. I've been saying a lot of words today. An asymmetric surface, is like a pencil. Okay, if I flip it upside down, it's something different. Okay, an aperiodic surface is one in which you form a sequence with a whether it's a waveform or a reflection phase grating. The first one looks like that. The second one you flip. The third one may flip or not flip depending upon the optimal binary code. And you can even do that randomly. I mean, it's nice to use the optimal binary code. But so that's the difference between an asymmetric surface and an aperiodic surface. And the waveforms are capable of being modulated by flipping. Both the waveform and the bicubic. The bicubic is two-dimensional, the waveform is one-dimensional.
Well, perfect, Peter. We don't have any more questions.
Okay.
But thank you very much for your time. We are extremely honored for having you here. As I told you previously, the presentation, you can imagine how much people have been following for your work for so many years, and how many, how much you have contributed to our territory because of your extensive knowledge that we have seen in your publications, in your books, and your presentations. So thank you very much for sharing with our chapter. And I'm sure that Mariana want to share some words also.
Mariana, if you don't mind, let me say one
Go
thing.
ahead.
I just saw a message from Jamie Angus, who apparently has joined the presentation. And I can't tell you how instrumental Jamie has been in developing the whole modulation scheme. Both Jamie and Trevor Cox have been instrumental in everything that I've done. I couldn't have done it without either of them. So thank you, Jamie. I'm sorry, Mariana, for cutting you off.
Don't worry. I was going to echo what Andres was saying. We thank you very, very much for your participation, for your presentation, for the contributions over the years. I was going to ask if you're active on LinkedIn or some other platform that we can keep the conversation going. If people still have questions, if they have a post on our page, could you see that, or do you communicate mostly via email these days?
Jamie Angus just sent me a heartfelt thank you.
We can invite Jamie to join.
So I have a LinkedIn page, and Andres joined the network, so he knows, he has seen it. Is that an answer to your question, Mariana?
To the LinkedIn network?
Yes.
Sure. If we're encouraging people to use the platforms to just keep the conversation going. So
yeah,
to know that you're reachable through that is helpful.
Oh yeah, absolutely. And if they want to, there's the Jamie Angus.
I'm muted. Sorry. Hi, Peter.
Hey.
Lovely talk. I really enjoyed that.
Well, as I mentioned, you were very instrumental in my life.
Yeah, I think you wished I would have patented them. Although, I think one of the interesting things is I remember when I first introduced it, you and Trevor, I think, came up with the idea of making the asymmetrical version so that you really could just turn it upside down.
Yeah.
That was kind of neat. That was really neat. So,
well, that was just a practical way of.
Of course, you only need one inventory.
Exactly. Yeah. Wow. It's so good to see you. I actually saw you on a presentation by. Oh my goodness. I'll have to email you. I can't think of the name of the presentation. But
It wasn't on floating point numbers, was it?
No. My mind is a blank. I've been talking for too long.
Yeah. Well, you've been working hard for an hour or so. So yeah.
Yes, we don't need to keep you any longer. Just wanted to bring Jamie up and say hi.
Oh, that was nice of you.
Thank you, Mariana.
And by the way, thank you all for such kind words. We all work in isolation. So it's good to know somebody's listening.
Yes, we absolutely are. We will send the link. We will share the link with the recording in case someone wants to reference something in English or Spanish. Hopefully that will be available for everyone.
Okay, wonderful.
And yeah, up until the next time.
Okay, very good. Thank you all.
Thanks again.
Take care,
Jamie.
Peter.
Thank you, Jamie.
Yeah, thank you, Andres and Mariana. Thank you, and Brian. Oh, okay, take care, everyone.
Thank you.